Good afternoon. My name is Brian Johnson. I'm the CEO and co-founder of DivvyCloud. Thank you all for coming out this afternoon, and I'm excited to dive into running Kubernetes cross-cloud. So the first question you might be asking is, why is DivvyCloud doing a webinar on cross-cloud Kubernetes? Well, we are best in class at enforcing compliance, security, and governance policies inside of cloud infrastructure. Things like ELBs and things like EBS volumes and instances and security groups, all making sure they remain compliant and secure and adhere to your company's governance policies. That's really what we focus on, and we've been very good at it over the last couple of years. As we talk to our customers, we learn more and more of them are moving to containers and serverless. So we are going to be broadening our scope of policy enforcement into containers, into serverless, which means there's just a lot more to deal with, a lot more moving parts, and we need to make sure we became experts in this space. One of the things that comes up on a regular basis is, how do we being a customer, deploy Kubernetes across multiple clouds? So we decided we'd do a research project, learn about ourselves, and come up to speed with the best practices and how it works. So today we're going to walk you through how to deploy a Kubernetes cluster across multiple clouds. We'll talk a little bit about the details, about the different technologies necessary to make that happen. And then we'll talk a little bit about the problems with running this in production, future opportunities, and of course, what this all means for the enterprise. So for those who aren't familiar, just a quick overview on Kubernetes. Kubernetes is essentially a container orchestration platform. It is not a container runtime, meaning it doesn't replace Docker. Docker is actually what Kubernetes uses on each node to run the containers. Kubernetes is in charge of deploying the containers to the specific nodes that have capacity or where they need to be based on labels or tagging. It can also handle dealing with the software-defined networking layer that allows the containers to talk to one another. It can do things like load balancing and so on and so forth, all inside the Kubernetes cluster. What Kubernetes is not, as I mentioned before, is it's not a runtime. You still have Docker sort of underneath the covers running a lot of these containers. Now that might change in the future as Google begins to bring out more container runtimes like gvisor and things along the lines, but for now, Docker is still a required component. So why cross-cloud? Well, first and foremost, I'll refer to the business aspect. A lot of businesses don't want to be locked in to a vendor. We all played the Oracle game. We know how painful that can be when you get locked into a 10-year contract. We all did the data center game for the exact same problem. We all know how painful it can be locked into a data center contract for a long period of time, and it doesn't provide you the flexibility you need as an enterprise. Furthermore, you really can't do good price negotiation if they know they got you by the tail. You can't leave their environment, right? So avoiding vendor lock-in is just a good business thing to do, ensuring that the cards are on your side of the table, that you have the ability to do negotiation you need, ensure best price, to ensure that you are protected, and ensure that you can make the best business decisions. Another reason to do cross-cloud is for best-in-class services. These providers are beginning to commoditize, meaning that the infrastructure layer is becoming the same across all of them. And a server is a server is a server, a load balancer is a load balancer, a load balancer. They're all generally the same and operate the same. What is beginning to differentiate a little bit is things like Google focusing in on AI and machine learning. Amazon has some incredibly great database service technologies, RDS, and some of their other things like DynamoDB and so on. Another reason you might look across cloud is for stability. Cloud outages do happen. I think last year somebody took down all of Amazon East Coast by running the wrong rm-rf command on a node. These things will happen. The reality is technology does fail, but people fail way more often. So we're likely to see more stability issues as systems become more and more complex. So it's important to spread yourself across multiple clouds to ensure that your application is still up and running and making you money in the event that one of the cloud providers goes down. And then finally, security. This is sometimes overlooked from a cross-cloud perspective, but we're seeing a lot more ransomware out there. We're seeing a lot more of people being taken hostage if their Amazon account is compromised, or something along those lines. So you need to make sure you spread yourself out so in the event that you are compromised, it provides you the ability to protect yourself and isolate the area that's been compromised a little bit, allowing you still to maintain your running applications and deal with the situation in the other cloud provider. So Kubernetes is going to make all this possible because it allows for very easy application portability. You can move applications from one server to the other server. In fact, the Kubernetes cluster is going to be doing it all the time for you as a part of the orchestration layer. So if this is what we're going to do, how do we go about doing this? Well, let's dive right in. So this is what our application looks like today. I've gone and pre-configured an Amazon environment and a Google environment, both with a VPC. One, I think Amazon's got the .200 and Google's got the .201. They have DNS and the internet connectivity and everything you would need necessary to run. And this is what it would look like if you deployed Kubernetes clusters in each one of those environments. You'd have independent load balancers, independent kube apps, and Kubernetes clusters, independent databases, and so on. But of course, we want to take it to the next step. We want to link these networks together, and so that we can deploy a Kubernetes cluster across both VPCs simultaneously. So how do we go about doing that? Well, we're going to leverage some of the native functionality inside of Kubernetes inside of Google Compute and in Amazon today. They both have very robust VPN solutions, allowing you to link VPCs together over IPsec or a couple of IPsec tunnels, all encrypted traffic, and making it completely seamless to the users without having to require you to launch a single open VPN server or anything else like that. So how does that work? Let's talk about the technologies you'll need to do this, and then we'll go and demonstrate it. So setting up a VPC peering or VPN connectivity between the two clouds requires you to use a few pieces of technology inside of these providers. On the Amazon side, we're going to use the virtual customer gateway. Virtual customer gateways are essentially like endpoints, right? They are the VPN endpoint that the VPN client is going to connect to. You think of it like a VPN concentrator. The virtual private gateway acts more like a router. It's what glues together the virtual customer gateway and the VPC. And of course, then there's the VPN connection, which acts as sort of a logical description of a VPN connection. It links together the virtual customer gateway with the virtual private gateway and creates a holistic VPN endpoint. And then, of course, we'll have to do some routing in order to make all this work. On the Google side, we can create a VPN connection, which again sort of encapsulates a lot of what I just talked about. We will need to provision a specific elastic IP address. I'm calling this out early on because it happens early on in the video. I pre-recorded this part of the demo, where we have to go and provision an elastic IP address. And the reason we need to do that is because we have to know the IP address ahead of creating the Amazon Web Services virtual customer gateway, because the elastic IP address on the Google side is the IP that all traffic will be seen as coming from the Amazon side. So it's going to be our internet routable IP address that traffic flows out of Google and into Amazon from. And then of course we'll create the VPN tunnels here. So let's go and get started, jump into this pre-recorded video, and I'll talk through it as the video goes on about how to create this. Okay, so as you can see here, we have an Amazon console on the left and a Google console on our right. So first thing I'm going to do here is I need to go and provision that elastic IP address that I spoke about earlier. We need to just provision it and reserve it. It just doesn't need to be attached to anything. We need it because we're going to use this IP address when we're configuring the VPN connection on the left-hand side in the Amazon platform. This IP address is the routable IP address that Amazon's going to see when Google is attempting to create the connection to the Amazon VPN concentrator. So the next thing we do is go down to the VPC on the Amazon side, now that we've provisioned the IP address. We're going to go to the VPC and we're going to go ahead and create a customer gateway. Now again, the customer gateway is like the endpoint for the VPN connection. It's what we're going to connect to. We're going to name it, and as you can see here below, we have the IP address. Now we're going to grab the IP address I provisioned earlier. Again, this is a security feature. Amazon just needs to know, hey, what IP address do I need to accept connections from? Okay, now that we've created that customer gateway, we need to go and create a virtual private gateway. Now, as you remember from earlier, we were talking about the fact that the virtual private gateway basically acts like a router inside of the VPN connection, ensuring the traffic goes to and from the appropriate subnets. So we're going to go and create this virtual private gateway, and in a moment we're going to attach this virtual private gateway to the appropriate VPC, ensuring that all traffic that comes in gets routed to the right VPC. All right, now let's go and associate it to or attach it to the right VPC. I've already set up this cube network. That's the 192.168.200 network. All right, it's attaching. Now, the last thing we need to do here is go down to the VPN connection. We're going to create this VPN connection. We're going to name it. And again, this VPN connection acts like the glue between the virtual private gateway and the customer gateway, ultimately the VPC. We're going to set up some static routing. And we need to set it up so that all traffic on the Amazon side that wants to talk to Google goes to this VPN. So let's go make sure we remember what the subnet is. That's right, it's 172.168.201. So it's 201.0/24. All traffic trying to reach that subnet should be allowed to go through this particular VPN connection from the Amazon side. Okay, now we're going to download the configuration. This configuration is just a text file that provides information on the two IPsec tunnels that we're going to create from the Google side. It provides information like what IP addresses to connect to and what the pre-shared key is. So now that we've got that, I've got that open off screen here so I can pull the information as necessary. We're going to go to the Hybrid Connectivity tab and go to VPN. From here, we'll create the VPN connection. Now, I did this earlier, so you're going to see the name for Cube VPN is already populated here. We're going to select the Cube network, which is the 201.0/24, make sure in the right region. And here, we're going to select the IP address that we provisioned earlier. As you can see, this is what the router is going to use to talk out from Google. We're going to then create an IPsec tunnel. I'm grabbing some information off screen here. I'm going to grab the remote IP address of the AWS of one of the two AWS IPsec tunnel endpoints. We're going to go and grab set the pre-shared key version, and we're going to go grab the version number itself, the key itself. Once that's in place, we're going to set up the route. Now we're doing the same thing as we did earlier on the Amazon side, but on the Google side. Anything that needs to go to 172.16, and I'll make sure here, .200, I believe, yep, .200.0/24 will be allowed to go through this particular tunnel. Let's get that set up. Cool. Now again, remember we are going to do two tunnels because that's what's exposed to us. This is really for fault tolerance purposes. So I'm going to get all the same information, but for the second tunnel from that same text file, including the remote peer address, the pre-shared key, and then we will set a route up again. As you can see, again, we will do 172.16.200.0/24. Okay, so we are all done. We've configured both tunnels in the overarching VPN connection configuration. And now when we go back at AWS, we're going to pull up that VPN, and we're going to wait for the connection to be established. First, we're going to see it go into a handshake where it does its initial handshaking, and then we will see the two connections come online. As you can see here, we have the IPsec tunnels, and then, of course, the Google VPN gateway, which basically is the same premise, right? It acts as a router that attaches to itself to these tunnels. So we're just going to wait for a moment while these come online. It can take a little bit of time. Okay, so we see now that the VPN tunnels have entered a handshake. They're still down on this side, so we're going to give it just a little bit longer. We might refresh here in a second. There we go. So we see that at least one of the two tunnels is up and come online. Still in down state, and we'll wait over here. It just takes a moment. Sometimes Google's console takes a while to refresh. We may just refresh the window. Okay, so we see that both tunnels are now established. So we have successfully linked together a VPC inside of Amazon with a VPC inside of Google. Now on Google's side, we don't need to do any more routing configuration. It's all sort of done for us behind the scenes. In Amazon, we need to go over and make sure we statically call out the routes that are associated with the Cube network subnet. Even though we've done that once before, the previous route setting was really about permission. It was about saying this is what can route through here. Setting up the route table actually does the route. So here we're going to say, hey, look, anything going to 201.0 on this particular subnet needs to go through that VPN gateway. And then we're also going to set up a second route to make sure that the servers inside this network can talk to the world by going through the internet gateway. Totally separate concept, not related to this. Okay, we are all set. We have created VPN connection, we've set up routing, and now let's test some connectivity. Let me switch over to another window here real fast. All right. So what we're going to do real quick is we're going to ensure connectivity between the two instances. On the left, I have an instance that's running inside of Google. And on the right, we have one running inside of Amazon. I don't have ICMP as firewall rule allowed, so we're just going to basically telnet to the SSH port on both of these boxes and ensure we see the banner. You can see here we have the appropriate IP addresses, 200 and 201 respectively. So let's real quick try and telnet to each other on port 22. Then there's the OpenSSH banner. Fantastic. So connectivity is allowed in both directions. And same here. So we're good. So we basically have now a network where servers inside of Google can talk to servers inside of Amazon over a secure VPN tunnel linking together both VPCs without having the instances or servers themselves having to be configured in any special way. I could deploy 100 servers in both of these VPCs and they'd be able to talk to one another. All right, excellent. So let's get on to the Kubernetes part. So what's next? Now we need to deploy the K8 cluster. K8, by the way, is because it's the letter K plus 8 more letters than S for Kubernetes. So step 1, we need to do the kube admin init. This sets up the actual Kubernetes cluster. Then step 2, we need to install Weave, which is a software-defined network. There's actually a large number of software-defined networks that are supported inside of Kubernetes, but this is the easiest one to deploy. So we'll talk a little bit about the software-defined network component and why it's important. So right now, what we have is our current setup with these two VPCs that are connected. And again, we have Kubernetes capabilities in both of them, but we haven't actually brought or built a Kubernetes cluster that's going to span both these VPCs yet. So let's go ahead and talk about what that's going to look like. In order to accomplish that, we need to create a Kubernetes cluster that spans both VPCs and leverages a software-defined network that layers on top of the host network that allows containers inside the different Kubernetes nodes to talk to one another without having to worry about which host they're on and do they know which host IP they need to connect to and so on and so forth. Software-defined networking inside of Kubernetes provides a lot of flexibility. It means that containers can move around very freely. It means that security can be controlled inside the cluster instead of on the host level. So it really provides a lot of very nice elements. But there's also some downsides. We'll talk about that in a little bit. It actually makes it a little complex to communicate with containers inside the Kubernetes cluster. For that, we'll use an Nginx load balancer, but we'll get to that in a moment. So let's go ahead and set up our Kubernetes cluster. So let me open up a window here. Let me create these 4 windows. All right, switch over. Okay, so we have these 4 windows here. Now this is a setup where we have 4 nodes. On the top left-hand side, we've got our Google master node, so I'll be referring to as the Kubernetes master. And on the right and bottom, we have 3 other nodes, will be sort of our worker nodes. Now the first thing we need to do is run the kubeadm init command, which is going to allow us to initialize the Kubernetes cluster. Now I'm highlighting this IP address here just so I can call it out. This is a configuration option that allows me to say that my laptop can connect to the Kubernetes cluster inside of Google or Amazon or wherever, utilizing the configuration file and cert that is being generated right now. If I didn't supply that, then when I tried to connect, it would reject my connection because I wouldn't be connecting to the 172 IP address. All right, so the first thing I need to do after that is I need to copy over the config file it gives me. All right, fantastic. Now we're going to take this kubeadm command and set it off for later. This is the command we're going to run when it's time to have the other nodes join the Kubernetes cluster. But before we do that, of course, we need to deploy the Weave software-defined network. Now you can see here, I've just run a single command. There's a kube control command you run to get the YAML that basically deploys Weave. As you can see, it's very straightforward. Once it's deployed and running, we can look and see that the Kubernetes master node is running. Now we're going to run this watch command real quick so that we can keep it up on screen. And this will show us the status of the Kubernetes at 1 second intervals. Now it's time to go ahead and have the other worker nodes join. We're going to copy and paste that kubeadm join command. And there we go. That's all we have to do. It now has joined the network. All 3 of those nodes have joined. Now I did that simultaneously to save on time, but of course you wouldn't have to do that necessarily. Now we'll sit here for a little bit and the nodes on the left-hand side there will become into a ready state, sort of, on their own. It takes usually between 10 and seconds to a minute, somewhere in there. It just depends on the traffic, how long it takes to spin up containers on each individual node, so on. And so what's happening right now is that each node is spinning up containers that is connecting to the Kubernetes cluster. And once that is done, the next thing it'll do is basically join the software-defined network, allowing for these containers and any containers deployed on top of these systems to communicate with one another over the Weave SDN. All right, so we have all the nodes up and ready, and we are looking good. I'm going to reset these windows for later use. Fantastic. All right, so now it's on to the fun part. It's time to start deploying software onto our Kubernetes cluster. In order to do this, we're going to use a piece of technology called Helm. Helm is essentially a package manager for Kubernetes. In fact, it was a part of the Kubernetes project until recently when it was moved to be maintained by the CNCF, which is basically a giant cloud consortium of sorts, comprised of Google and Bitnami and Microsoft and so on. So anyways, if you want more information, feel free to go to the website. So now we're going to deploy Helm to our Kubernetes cluster. Now the way this works is I'm going to use the Helm command to initialize the Kubernetes cluster by deploying what's called the tiller pod. A tiller pod is just a container that runs inside of the Kubernetes cluster that allows us to talk to it. The Helm is essentially just a client that talks to tiller, which is a server. And when then Helm says I want to deploy these applications, it talks to tiller. Tiller goes and gets the application configuration and actually does the provisioning. During this process, what you're going to see is I'm going to use a YAML file to configure the service account for tiller to use, giving the tiller pod the ability to communicate with Kubernetes from inside of Kubernetes so that they can do these types of deployments. So the first thing we're going to do here is I want to do a quick check to make sure that I'm on my laptop now. So I need to make sure that I can, in fact, communicate to the Kubernetes cluster. It looks like everything is good. So the next thing I'm going to do here is just show off that role-based access control YAML file I talked about. You can see at the top, I create a service account. At the bottom here, we're creating a cluster role binding. Essentially allows this service account to have cluster-wide permissions. Next, we're going to go ahead and deploy. I don't know why it does that big space. We're going to go ahead and do a create of that particular config. It created the service account and the cluster role. And now we're going to initialize. So we're also going to call it specifically that it should use the service account tiller. All right, so now the tiller pod has been deployed into Kubernetes, and we'll show that off here in just a second so you can check on it, make sure it's running. We're going to give it a little bit of time to come online. And while we do that, let's go ahead and dive into the next phase. So the next phase is about creating that software or using that software-defined network. As it stands right now, we have basically a Kubernetes cluster deployed across multiple systems, deployed across 2 VPCs, one in Google and one side of Amazon, and we're using the Weave software-defined network to sort of make a network that all the containers can sit inside of in terms of Kubernetes and communicate with one another, and all of that traffic is being encrypted and passed over the VPN tunnel that we created earlier. So there's a problem with this, though, and the problem is that it's not actually super easy to talk to the containers inside the Kubernetes cluster. As I mentioned, the containers are a part of this Weave software-defined network, so they don't actually have an IP address. It's on the 172.1.6 space. So it's hard to communicate with it. You need to have some sort of bridge, load balancer, or proxy to allow you to connect into the container and route traffic in. For that, what we're going to use today is an Nginx controller or a load balancer. The load balancer will have 2 IP addresses associated to it, one on the 172 network and one on the software-defined network, which I think is like a 10.0.0.0 network. So what do we do with this? Well, we're going to deploy an Nginx controller. The Nginx controller is a Kubernetes Nginx instance that allows you to deploy Nginx as a container onto multiple nodes inside the Kubernetes cluster. It will use 2 services of Kubernetes to do this. One is called Ingress. Ingress is a Kubernetes service that essentially acts like a configuration element. It essentially provides information to Nginx about how to do routing. Now, this is layer 7 routing, so it will provide for URL path routing. And it's going to basically say, look, anything going to /admin is going to go to the admin service, which is subsequently going to route to the containers related to the admin application. Well, let's talk about the kube service here. A service is another Kubernetes concept. This is actually more like an internal load balancer. A Kubernetes service acts by exposing a single internal port, so on that 10 dot network, that you can connect to, that will then take all the traffic and basically route it or balance it between however many containers you have that are associated with this particular service. So how this all comes together is that the Nginx controller is a Nginx container that is run on each Kubernetes node that has a 172 IP address and a 10 dot IP address. It uses the ingress configuration element, that's a Kubernetes configuration element, to figure out what service it needs to route traffic to given the path. And then, of course, passes the traffic onto the service. The service then passes that traffic onto the different containers on the Kubernetes cluster. So Is that simple enough, right? Clear as mud? Fantastic. So let's go on to the next stage, and we're actually going to deploy this Nginx controller. So here we're back on my laptop again, and what you're going to see me do here is I'm going to deploy Nginx controller using Helm. Specifically, you're going to see me use a flag that is referred to as the sort of the network host flag. What this tells Nginx to do is to make sure that it listens not only on ports on the internal Kubernetes cluster, so the 10 dot on the software-defined network, but also to bind to port 80 on the host itself, so the 172 IP space. So let's go ahead and get started. And this is a pre-recorded little section. We have a Helm list just to make sure Helm is running. It looks like it's okay. We're going to go ahead and check to make sure all the pods are running. Tiller is up and running, and we're in good shape. So we're going to go ahead now and go install Nginx. And you're going to see me use that flag, that host network flag, here in a moment. And then you're going to see me use a replica count flag. A replica count flag just says how many of the Nginx controllers we want to run. Well, we have 3 worker systems, so we're going to have 3 controllers. All right, so we are deployed. Now, if we scroll up a little bit, we should be able to see the containers. They're not going to be fully running yet. They're going to be in the creating process, but you can see we have 3 containers plus a 4th, which is a default backend. Basically, anything that doesn't get routed to a service gets routed to the default backend. Let's take a look at the pods real fast. Oh, wait, don't need the namespace. Let me get rid of that. Cool, so there they are. They're the running pods, or the running containers, rather. And you can see that a couple of them are online, a couple of them are still waiting to come online, so that's fine. But before we move on, I want to talk about that section there in the center, which says an example ingress that makes use of the controller. So this is what an ingress policy looks like, or configuration. This is what you would actually deploy to Kubernetes, and it would make up of an ingress. You can see that it has rules. Rules have a host. Inside that host, you specify a protocol, you specify a backend that's supposed to connect to, and you specify the service name and the service port. So this is the Kubernetes service by name, and the Kubernetes service and what port that particular service is listening on. And then, of course, a path. So right now I've got /, which will cover everything, but I could do /admin/, I could do /UI/, whatever I want to do to send traffic to different containers. And again, the bottom there, you can see there we have more host section, but as this relates to deploying TLS and SSL certs, so you can do SSL encryption. All right, so we're going to move on to the next piece. This is where stuff starts to get fun. Let's talk about what we've got. What we've got now is we have a Kubernetes cluster deployed across multiple VPCs, one in Google and one in Amazon. We have a Weave software-defined networking that's linking all those containers together in a single network. That's all being run over an encrypted VPN connection. We have Nginx controllers deployed that's going to bridge the host network and the internal Kubernetes software-defined network. So now we are going to, at a point, we can deploy a piece of software. So we're going to go and deploy DivvyCloud because it happens to have a Helm chart. So let's do that. So here you see we're back to, we have 3 windows. We have Amazon on one side, we have Google on the other side. On the bottom, I'm going to be running commands. And what you're going to see here is I'm going to deploy DivvyCloud onto these systems. Once, as a part of that, I'm going to create a local host entry in my host file so they can resolve the appropriate DNS name and then send it to any one of the nodes you see here, because all of them can accept traffic and all of them can process traffic to the appropriate container. I'm going to use my host file because it'll take too long to do DNS in this presentation. So first we're going to do Helm list. We're going to look and see that the Nginx controllers are in fact running. Everything is good there. Now we're going to go modify the Helm chart, and we're going to update the configuration. Right now, cube.divvycloud.io is how we install DivvyCloud and what it'd be listening on. We're going to go and change that to crosscube just for the purposes of the demo. And we're going to go install DivvyCloud. I'm going to provide it a namespace, DivvyCloud, and a name, DivvyCloud. All right, so now it's easy to identify and work with. So you see I've deployed all the containers are out there running. You see the node port and cluster IPs. And here in particular, you see that I've got the ingress rule for crosscube.divvycloud.io, meaning that if you go to that particular namespace and associate with one of these IP addresses, it will route you to the DivvyCloud application. So let me go and do that. Let's grab one of these IPs. This one looks good. Sure. Okay. All right. Let's just make sure it resolves, make sure everything's okay. I realize it's a resolve.conf file. It should just work, but all right, good. So now we know that we can resolve to that IP address, and we're just going to wait for a little bit to make sure the container comes online. It takes just a moment. All right, let me check the status here real quick. We're just going to curl this. Go to status. Cool. All right, so if we now go to this URL, which again is mapped to one of those nodes at this exact moment, go there and voila, DivvyCloud is up and running. If we change the IP address in the host file to any of the IPs across any of those nodes, with the exception of the master node, which doesn't actually have any containers running on it that's related to our service, you would be able to get to the DivvyCloud application. So there we have it. We officially have deployed DivvyCloud onto a Kubernetes cluster that is across multiple clouds simultaneously. Now let's talk about, we're done with the demo part. I'm going to cover a few more elements here, specifically like how would you do this in production? Well, clearly a host file isn't going to work. So you would use some sort of weighted DNS, right? You would have something where we're doing a DNS round robin or something along those lines where traffic is being sent to each particular cluster. This, of course, has some problems. We'll talk about that in a little bit. There are other options related to this as well, and we can chat about those in the question and answer section. I didn't put together a slide for it. But there are some cloud-agnostic load balancers out there like Cloudflare and that kind of thing. So what are the problems with doing this type of setup in production? Well, let's talk about that a little bit. So number one, as I mentioned, weighted DNS isn't exactly the best option. I mean, it works, certainly, right? You can do some sort of round robin, you can do weighting, you can do all sorts of different things. The problem is that DNS takes a long time to propagate. So if AWS goes down or Google goes down or whatever, you're going to have users having a suboptimal experience because they'll be going to a dead website for as long as it takes DNS to update, which could take a while. Unfortunately, not everybody sets their DNS caching to like 1 minute. So it'll work. Certainly it'll get the job done, but you might want to investigate Cloudflare. You may want to look at you leveraging the Google load balancers specifically, which have the ability to talk to different IP addresses that are not in Google. Certainly some things to look at there. VPN, doing all the traffic on the back end over the VPN, this is going to have some overhead, right? 95% of the applications out there are never going to notice this over. The latency between these two providers is so low, they're basically connected directly. And furthermore, for web applications and the processing you're going to see there, the encapsulation time and decapsulation time is so minimal, you won't even notice. Now, if you're doing super high throughput traffic, so it's like high throughput UDP or something like that, it may not be the best option. So you may want to look at some of the other ones out there. There are some other VPN solutions out there that would require you to do more configuration on each individual node, but would be a little faster. Of course, as you saw, it is not the easiest thing in the world to set up and manage. You have to sort of a lot of moving parts and sort of understand a lot about each provider and how they operate and so on and so forth. So, this is not a great thing from that perspective. Now, of course, if you had the DivvyCloud software, this would be less of a concern because you would ensure that you had guardrails, so no one could do anything that would be completely insane or put yourself in a compromising position, such as leaving a port open or something along those lines. Just, a little plug for the software. And then finally, IAM complexities. We didn't talk about IAM too much today, which is the identity access management. This is basically some concepts that allow you to have nodes inside of each cloud and grant them access to cloud services such as machine learning or DynamoDB or whatever. But as you can imagine, when you want to deploy a container that have access to a particular Google or Amazon service, you would need to ensure the container is running on a node that's inside of Google or Amazon. Now, this can be taken care of pretty straightforward with node selectors, which is a Kubernetes concept. It's really not that big of a deal to handle. However, it is a complexity you would need to take into consideration. So is this the most ideal way to set up a cross-cloud cluster? No, not really. I did this so that we could see the raw nature of how a Kubernetes cluster would work cross-cloud if you had one cluster. However, Kubernetes believes very much in a multi-cloud environment, if not just because of Amazon and Google, but also because there's a lot of enterprises that still run a lot of data center workloads, and quite frankly, there probably will be for some time to come. Cloud is not always cheaper and not always the best option, so you need to make sure you can create a Kubernetes cluster that works across multiple locations, whether it be put to public clouds or private clouds. That's very important to Kubernetes. As such, they've created cluster federation. Cluster federation is the ability to run individual Kubernetes clusters and sort of manage them in an isolated way, but then link them together using a federation control plane so that when you deploy containers, you're deploying to essentially one big cluster that's made up of a bunch of smaller clusters. If you want more information on this, please go check out KubeFed. So, last plug here. Look, there was a lot of moving parts here. Right? I've sort of talked about this jokingly a couple slides ago, but in all seriousness, it would have been very easy for me to make a mistake. In fact, I very well may have. After I go review this video, we'll see. But at the end of the day, if I had misconfigured a firewall, if I had done a whole bunch of other configuration that, quite frankly, I did ahead of time in terms of creating VPCs and, as you saw me do the VPN, making sure that I had the right IP address in there and so on and so forth, there were a lot of moving parts that I could have messed up. I could have gotten wrong. And so you really need to have guardrails in place if you want to allow your engineers to experiment and do research and development like I did here today. And that's really important as your organizations move forward to try and figure out how to remain at the cutting edge, to be productive, and to make sure you get your applications to market as quickly as possible. Cool. Well, I will stop here and take any questions anyone has. Hopefully there are some to dive into. Thank you all for listening, and I'll open the floor.